What's up, bitches? Today we're learning the diesel cycle. Now this cycle is a little bit complex, so I'm gonna really try to take my time and explain step by step everything, okay? Your diesel cycle looks like your typical simple Brayton cycle. From point 1 to 2, it's isentropic, and point 3 to 4, it's also isentropic. What does isentropic reaction mean? It means that when you're dealing with these 2 points, you can use these formulas over here. These should be usually in your formula sheet. But for this cycle, you're going to mainly use these 2 equations, okay? And K for air is 1.4. That's all it means. Otherwise, it's very similar to your Brayton cycle. From point 2 to 3, it's constant pressure. And then point 4 to 1, instead of being constant pressure like your Brayton cycle, it's constant volume. That's the catch. Otherwise, you have work in over here, work out over here. Whoops. Q in on top, Q out at the bottom. For your diesel cycle, from point 2 to 3, heat enters, but there's also work being done by your system. Okay? This is what the diesel cycle looks like. You should memorize this by heart. Or if you're allowed to have a cheat sheet, you should just copy this down for your diesel cycle. Now, it's a little bit more different than your typical cycles. Usually, you would use delta H to find Q's and W's, but for your diesel cycle, you can't use this. If you want to know why, it's because the diesel cycle, it's a closed system. So there's different laws. You know, there's the first law of thermodynamics. What was it? Delta U equals Q minus W. And using a bunch of ideal gas laws, basically you can't use delta H to find your diesel cycle. Instead, what you're going to use is Cp or Cv times delta T. Okay? Typically, you use Cp when there's constant pressure in a reaction, and Cv when it's constant volume in a reaction, okay? I'm going to tell you guys from right away, from point 1 to 2, the work done is equal to Cv times delta T, even though the volume is not the same. Why? Because using the ideal gas laws and everything, it's going to come back to this. You're going to see in a bunch of your solutions that they use this formula to calculate the work done from point 1 to 2. Keep in mind that you're dealing with air, so Cv is equal to 0.717 and Cp is 1.004. You should have this in your in one of your manuals or something. Another thing that you should remember for the diesel cycle, since it deals with the constant volume, a lot of the rules changes when you're dealing with problems like this. A lot of the questions, they're going to give you a compression ratio. It's R. It's basically the ratio between V1 and V2. You have to know this. Some of your questions, they're going to ask you for the cutoff ratio. Cutoff ratio. It's RC. And that is equal to V3 over V2. This question was in some of my my problems, practice problems, but it wasn't in my final exam, but you should just know it just in case, you know. Other than that, that's it. That's your diesel cycle. There's one more thing that you guys could know. This is the PV diagram for your diesel cycle. Now, personally, I never learned this by heart. You don't really need to know this if you've memorized the TS diagram by heart. But just in case if some of the questions or in your exam they ask you this, this is what the PV diagram looks like for the diesel cycle. All right, guys, I just picked a random problem from my problem pack. And we're going to solve this as an example, okay? Before I start, the problem gives us volume 0.5 liters. But by the way, the diesel cycle, you're dealing with pistons, okay? The question is giving us the volume of the piston. So it's useless. Even in in the solution, they don't even use this. So just be careful. Don't get tricked. If your professor's a little bitch and he uses these as trick questions, just be careful. And that's it. Okay, so the first thing that you do when you deal with a diesel cycle or any cycle problem in thermodynamics is you draw your TS diagram. All right, I drew everything, point 1, 2, 3, 4, all the works and heats involved, and I wrote CP for constant pressure, here constant volume, and isentropic. This way, it's like impossible to get lost unless, you know, you're retarded. But everything's over here. So the next thing that I do when I deal with these problems is I draw a table, P1, T1, and specific volume. I know usually you deal with like volumes, but the diesel cycle is a closed system. That means the mass flow rate doesn't really matter, okay? Because, well, what was it? Specific volume is equal to the normal volume divided by M. But you don't give a fuck about the M because it's just a piston. It's a closed system, and the mass flow rate is just gonna stay the same the entire time. There's no mass going in or out that matters in your calculations. So you could either use specific volume, which probably that's what you have to use, or the volume. But you can't mix both, okay? But to be honest, every single problem that I did with diesel cycle, I was using the specific volume and it was fine. So anyways, you continue drawing this table. All right, so it's giving us the inlet P1 over here and T1. So 95 to 90. And then it says maximum cycle temperature is 1800 Kelvin. Where's the maximum temperature? Oh, it's over here, 0.3. That's why the TS diagram is very important. And that's all we have. Oh, it's also giving us a compression ratio. R equals V1 over V2, 20. That's it. So let's start with point 1, okay? Point 1 to 2, it's an isentropic reaction. So you can use your isentropic equations. That way you can find P2 and even T2, okay? Well, let's find T2. T1 equals V1 over V2 K minus 1. Wait, sorry, it's V... No, sorry, it's V1 over V2. V1 over V2, we have that it's 20. So to find the T2, you just multiply... Well, you just bring this the T1 to the other side. So T2 equals T1, which is 290, times V1 over V2, which is the compression ratio, 20. And K minus 1, that's 1.4. K is equal to 1.4. CV equals 0.717. CP is 1.004. So that is 0.4. And then you get a T2 of about 961.2 Kelvin. So we're going to write this 961.2. All right. Next, we have both temperatures, so we can calculate the work done over here. Work in is equal to CV, which is 0.717, times delta T. So 961.2 negative 290. And that gives us 481.25. Again, you can use CV for this first work over here, even though the volume isn't constant, because like it's a closed system and like using the ideal gas laws and everything, like using algebra, it comes to CV times delta T. I remember my professor did the algebra in class to show us, but it's super long and complicated, and to be honest, you don't really need to know that for your exam. Just remember that over here. This one, it's CV delta T. All right, next. We can use the isentropic equations again to find the second pressure. Equals V1 over V2 K. So P2 is equal to P1, 95, times the compression ratio, 20, to the power of K. And that gives us about 6297.5 kPa. 6297.5. All right. Next, we can see that P2 and P3, it's constant pressure. So this is also equal to P3. All right. So now we have everything. Now, we have to find these specific volumes. To do that, I'm going to use the, what's it called? The ideal gas laws, okay? PV equals MRT, right? But we know that the specific volume, which is what we're using, is equal to the volume over M. So, sorry, this specific volume times P is equal to RT. So, specific volume at point 1, it's equal to R times T1 divided by P1. The R for your air is 0.287. Careful for the units. Times T1, 290, divided by 95. And that's going to give us a value of about 0.8761. 0.8761. All right. Next, using the compression ratio, R equals 20 equals V1 over V2. We find that V2 is equal to V1, 0.8761 divided by 20. And that gives us 0.0, where is it? 43805. 805. All right, let me clean this up real quick. Okay, so next to find, I'm going to try and find this one over here. What you have to keep in mind is from point 2 to 3, it's constant pressure, okay? So this times P, not 1, sorry, 2 times P2, using the ideal gas law, should be equal to this. And V times P3 is equal to RT3, right? That's the ideal gas law. So if we take this times P2 and divide by R, fuck, bro, RT2, because they're equal to the same. This is equal to 1. It's also equal to this, 3 over RT3. That's using the ideal gas laws. Since the pressure is the same, we could just remove this. R is also the same for air. So what we're left with is this. T2 equals V3 times T3. So specific volume at point 3 is equal to T3, specific volume at point 2, divided by T2. And we have all the values over here. Times 0.043805 divided by T2, 961.2. Giving us a T3 of about, where is it? Sorry, a V3 of about 0.08203. 0.08203. All right. Now, we have delta T at point 2 to 3. So we can find the work being done, which is equal to P times delta V, right? Because work is equal to the integral from V1 to V2 of P times dV, okay? Since the pressure is constant, we can use this exactly over here, but we don't have the volume. We have the specific volume, which I explained earlier that it's fine because there's no mass flow rate. So we can use this. Our pressure over here, it's 6297.5. And delta V, we're going to use the specific volume, 0.08203 negative 0.043805. Giving us a work out of about 240. Damn. Fuck, bro. Fuck this pen for you. 240.72. All right. To find Q in over here, you're going to have to use CP times delta T. Q in equals CP times delta T. But for Q out over here, you're going to use CV times delta T because it's constant volume here. And up here, it's constant pressure. This is just like an equation that you have to know by heart for your diesel cycle. So CP 1.004 times delta T. So 1800 negative 961.2. And that gives us 842.16. All right. Okay, next. There's just one last point left over here, point 4, and we have nothing. So what do? Well, you check that it's an isentropic reaction, okay? So you can use your isentropic equations to find everything. So we're going to use T4, T3 to find the specific volumes. V4 over V3, which is K minus 1. But since we're going from up to like if you go from 1 to 2, it's going to be equal to the the power is going to be K minus 1. But since we're going down from here, it's going to be negative. Otherwise, it won't make sense. Okay. if you see that, you don't need to memorize this, because if you just calculate this normally and you see you get a T4 higher than T3, obviously it doesn't make sense. You just put negative power. Anyways, T4 equals to T3, 1800, times V4 or V3, negative 0.4. V4, we check our TS diagram, and we see over here is constant volume, so we could just use V1. V1 is equal to V4, 0.8761. We're just going to use that. Where is it? 0.8761, 0.08203. Giving us a T4 of about 697.98 Kelvin. All right. 697.98. And that's it. You don't really need P4 to solve the rest of the problems, but anyways. We have our P3 over here. This is our maximum pressure, so this is done. W net. Oh, did we calculate V out over here? Oh, there's only one more V out left. W out, sorry. To calculate this part over here, you have to use CV again, just like a 0.1 V in over here. It's the same concept over here. It's equal to CV delta T. So, V out, W out, 0.717 times delta T. We're going from 0.3 to 0.4, right? So it's 1800 negative 697.98, giving us a V out of about 790.15. So W net is equal to W out negative W in. We have two W outs, by the way. So you do this plus the other work out over here, which we calculated over here. 240.72. Negative W in, which earlier I erased, but it was equal to, what did we calculate? 481.25. Giving us a W net of about 549.52. Right? Yes, 62, sorry. And the Q in is over here. So we could find the thermal efficiency with W net divided by Q in. 549.62 divided by 842.16. 16. Holy shit, this pen is ass. Giving us thermal efficiency of 65.3%. And that's how you solve your diesel cycle problems. Now, when I did, again, the most important thing is to know this TS diagram by heart. Once you know this, it's really hard to fuck up. But to be honest, if you're learning this for your final, personally, I didn't have the diesel cycle in my final exam. So if you're worried, don't be too worried. Like, there's a good chance you're not going to get it. But just in case, like, practice this. But bro, it's really not that hard. It's very simple. It's just a matter of practicing and understanding. I know it's very different from your typical cycle problems, but it's really easy once you get the hang of it. And that's it.